Welcome to Developing Ray Tracing Content on Mobile. This is a talk delivered by myself, Xandro, software engineer at Arm, Dong, senior graphics engineer at Tencent, and Ying Che, technical manager at MediaTek. To give you a brief overview of the talk, today we will first be introducing ray tracing, and then Tencent will give you a rundown of their Ray Query solution, which will lead into a performance guide on how they optimize their techniques, where we will then end with MediaTek giving us an overview of their SDK. Ray tracing is coming to mobile. Having started on machines with exceedingly high power budgets, it has recently trickled down to consoles where we are seeing games like Cyberpunk 2077, Spider-Man, and Resident Evil Village all have full ray tracing support. Khronos also officially released their full Vulkan specification for their ray tracing extensions at the end of November 2020, giving developers a clear guide on how to use the API and giving driver teams the insights on how to provide compliant implementations. With ARM also announcing hardware support for ray tracing, it is clear that it is no longer a possibility, but a reality. Well, what about right now? Even though hardware support isn't yet available on mobile, ray tracing is possible with the use of software implementations. This is important as it allows projects to start targeting their content early on and can begin to accustom developers to the Vulkan API and how they can write applications and games that make use of this technology. Since a software implementation isn't accelerated, we need a way to make graphics workloads representative and their frame rates sufficient. Because of this, there is a growing body of research alongside that is helping optimize Ray Query. This is significant for the ecosystem, as when hardware support does become available, these algorithms and techniques will still be relevant. They will help developers further utilize their power budgets and to deliver cutting-edge games and applications to their users. The first step that ARM took towards developing a software implementation was to build a library that could hook into the Vulkan calls for the functions that the acceleration structure extension uses. This allowed us to build an acceleration structure view of the scene that accelerates the ray tracing logic. The second step was to provide shaders that could handle the ray traversal calls. To do this, we wrote our own ray traversal algorithm in GLSL shader code and included it directly into the source. This meant the application was responsible for compiling the GLSL into SPIR-V and then building the SPIR-V into shader modules inside of our Vulkan renderer. This allows the application to trace rays into the scene inside the fragment shader. As you can see in the software stack diagram, the green sections are the additions one would have to make for their application to support ray tracing. They first must build and link their application against an acceleration structure builder implementation, where the developer can then either hook into existing Vulkan function calls or provide their own. Finally, they then have to add the shaders that perform the traversal logic into the actual application itself. This solution is clearly not a user-friendly one, as not only does it require two dependencies that each must be maintained in line with the application, but also it has to be integrated into each existing application that wishes to use it. That's why we took the next step of developing a software layer. A software layer is essentially the same implementation as before, except wrapped up into a layer object. This can then be provided to the Vulkan instance when you first load up your application, preventing the developer from needing to maintain different code bases and removing an extra dimension of compatibility. The layer can be added in the exact same way as validation layers, and it will provide the application with fully compliant Vulkan ray tracing extensions. The software layer provides the extensions that are required so that the application can use the Vulkan API. And as far as the API is aware, the driver can support these extensions. The software emulation layer slots in between the driver and the Vulkan API, providing a software implementation for the API so the application can perform ray tracing. This means the layer emulates the driver support, hiding away the implementation details from the API and the application. Therefore, the application doesn't need to worry about building and linking to third-party libraries, nor does it need to include any shady code. This allows developers to drop this layer into existing applications and let them focus on what really matters, the ray tracing. If you want to get involved or find out more, contact us at developer@arm.com. Here's a video of the ray tracing layer in action on a Mali S21 G78 device with Ray Query shadows. It is a demo developed in-house at Arm called Bonza, which is one of the ways we run representative real-world content on our chips. This helps us to both showcase Mali's ability and test to validate the underlying real-time graphics implementations. Here you can see an indoor scene where there are two lights that are casting shadows. The sun from outdoors, where you can see the shadows from the windows moving along the floor, and an indoor point light to help accentuate the shadow of the focal Bonza statue. We'll now give a few tips on how you can improve your performance using fragment shader ray queries. It's important that you only spend time on rays when it's necessary. Using the same shadow example, you'll likely have a scenario in your shader where you'll loop over each light for the current pixel and traverse through the acceleration structure to find an intersection. However, if you're using punctual lights, then you are wasting time when you can determine a pixel isn't going to be touched by the light at all. By finding the distance between the light position and the pixel position, you can compare this with the light's range to see if it's within its boundaries. If it is not, you can skip the ray query altogether. This makes point and spotlights efficient. Another tip to go with the first is to make sure that you set your ray max to the distance that you've just calculated to avoid the ray needing to be traced across the entire scene. The next tip is to skip pixels that are not facing the light at all. Since we've already generated our geometry in the gbuffer pass of our deferred renderer, we have access to surface normal information and can use the dot product of the surface normal to the direction of the light to determine whether the surface is facing the light or not. If it isn't, we can determine that it must be in shadow and skip the ray query call altogether. Lastly, you can skip pixels that do not have any geometry drawn to them at all. For example, the far plane or the clear value of your depth buffer. This is especially beneficial for outdoor scenes where most pixels towards the top of the frame can be just the skybox, something you wouldn't want to try and intersect with. Here are some further tips. Reducing the resolution of your application is a great way to immediately save on performance. In the case of generating a ray query shadow mask, you are casting rays for each pixel. Therefore, reducing the resolution can reduce the number of rays you are casting per frame. This can be done in two ways. The first is to reduce the overall resolution of the application. For example, on a Samsung S21 device, the native resolution is 2280 by 1080, which is quite high. An application casting 1 ray per pixel will mean you'll be spending nearly 2.5 million rays for any given frame. When you look at games such as Fortnite, they render to 1550 by 720. So reducing your overall resolution to something still acceptable yields a much cheaper 1.1 million rays, with not much reduction to visual quality. The other method is to use a separate shadow render target that uses a lower resolution, such as 50% of the main render target. Generate the shadow ray query mask and blur the results, upscale, and composite this with the full resolution image, and you'll be getting a similar result to soft shadows. I'll now pass you over to Dong, who will talk about Tencent's hybrid mobile rendering pipeline.
So thanks for the ARM and MediaTek. Hello everyone, my name is Dong Dong from Tencent Game, and it's my great honor to be here to demonstrate our progress on mobile ray tracing. For the next 10 minutes, I'll give the speech in 2 minute parts. First, I'll play our ray tracing demo and give a brief introduction for the techniques we used in the demo. Then I will give some performance guide when developing ray query application. So let's begin with the first part, the hybrid mobile rendering pipeline. And this is our demo. The whole scene locates at outer space, and the visual effect is enhanced by ray tracing. You can notice the shadow produced by the sphere light with soft and natural transition. Also, as you can see, there is ray traced ambient occlusion at the corner of each building structure. Now we are going to more details about the techniques in our demo. The whole rendering pipeline could break down into 5 steps. The first step, for those lights without shadow, we do cluster different lighting using on-chip memory. After the first step, lighting, depths, and normal buffers are resolved. Then we accumulate shadow lights using requerying. Third step, we dispatch a full screen pass for ray traced ambient occlusion. Fourth step, a shading pass is applied for compositing direct light with skylight, which is attenuated by ray traced AO. Finally, post-processing is applied for the scene color texture. As mentioned above, we use on-chip memory to reduce read-write bandwidth consumption for different lighting. At the beginning of each frame, a light list is built for each cluster using Compute Shader. After that, we invoke a render pass, which consists of 3 subpasses. The first subpass is gbuffer pass. Secondly, we blend decal with gbuffer. The third subpass is a full screen pass, within which we locate the cluster for each pixel and loop the correlated light list for non-shadow light computation. Now let's take a look at ray tracing features. This is our soft shadow effect with and without denoiser. The left figure is one SPP shadow generated by importance sampling, and the right figure is the final soft shadow result filtered with our shadow denoiser. Next section, I'll show how we achieve this. For shadow lights, we firstly render the screen space shadow mask with requery, then use a denoised shadow mask for light computation. The light computation is exactly like before, which means each local light would be treated as a point light for simplification. For the shadow mask computation, we assign a sphere radius for each point light. Then samples would be chosen within the light cone randomly with Houghton sequence. Once we get the noisy shadow mask, our spatial denoiser is applied. Firstly, we build a shadow mask variance estimation with 3x3 sized kernel. For region with high variance, we treated it as penumbra, which need to be filtered. For region with low variance, we just passed it through. The spatial filter is invoked within workspace, and the radius is derived from both ray head distance and the shadow mask variance. To prevent overblurring, we use edge stopping function based on the depth and normal difference between nearby pixels. As you can see, the penumbra radius could be calculated by average ray head distance of samples. By the way, our spatial filter is anisotropic, which could provide more visual pleasant shadow transition compared with isotropic filter. And this is our ray traced AO with and without denoiser. Ambient occlusion is an important visual clue for inner structure. It's also a simple way to approximate global illumination. For non-sky pixels, AO samples are drawn by cosine-weighted importance sampling. For each pixel, a chip remarching algorithm could firstly be applied on screen space to find a occluder. If found, we don't need hardware ray tracing anymore. If failed, then we dispatch a query. After the ray traced AO pass, a spatial filtering kernel is used, similar to soft shadow denoiser. During the period of developing demo, some best practices of performance are acquired. Here are some of them. First, with Vulkan requery pipeline, one can easily call meshes by instance mask. For example, if you just want a mesh to cast a shadow, but not to be reflected, then you could just mask out this mesh with bit flag when doing reflection computation. Second, Unlike rasterization-based algorithm, frustum calling is not available for retracing acceleration structure. But acceleration structure traversal is a bandwidth-limited operation. You need to carefully keep the memory footprint as low as possible for AS. Fortunately, you don't need to build the top-level AS from scratch every render frame, but instead, you could build incrementally. So in order to remove instances with little influence on final image, you can use some heuristic strategies to add or remove instances. One practical strategy could be the solid angle subtended by instances to the view camera. Once the solid angle is below a threshold, then it should be removed from the top-level AS. An extra bonus of retracing pipeline is instancing. Multiple instances can share a single bottom-level acceleration structure without additional memory consumption. That means you should always use instancing to build the scene if available. To summarize, we've implemented requery on mobile device. The retracing effects are appropriately integrated with our existing rendering pipeline. With the help of our mobile retracing denoiser, image quality by retracing are greatly improved. At the same time, this makes it possible for the overhead, which could be affordable even on mobile device. So this part is all of the Tencent Games trial on mobile retracing. Now I'd like to handle this presentation over to MediaTek. Thank you.
Thank you, Dongdong. It's amazing retracing technology sharing. Hi, I'm Louis, and I come from MediaTek. Today, we introduce the MediaTek Retracing SDK that can enable the retracing capability on our next generation chipset, Dimensity. MediaTek Retracing SDK includes two major parts: the retracing functions and tools. The SDK includes the basic function block for developers to build all kinds of retracing effects, such as reflection, refraction, and shadow. First, our ray triangle intersection test API is in the form of requery, which is defined by open standard. Developer can use it directly in their existing shader code. Our requery API are compatible with Vulkan extension. To achieve advanced retracing effects, our framework also provides some post-processing functions to improve the quality and the performance of retraced results. Our SDK also provides some tools for developers to debug and providing the program. In order to use Vulkan APIs, developers need to take care of the dependency between lots of commands and the resources. It's very complex and hard to maintain. Our tool can help developers by giving a graphical view of this information and reduce the time to debug. Here shows some ray trace results that are built by our SDK. The ray tracing application could be classified into three major categories by computing cost. The first one is the lightweight application. A ray trace reflection, and shadow effects can be achieved in real time. In the first image, the combination of reflection and refraction are shown on the crystal bunny and the teapot. In the second image, the virtual bunny object can interact with the real environment as long as we have the image provided by camera. The second kind of ray trace effects are more advanced. They usually require the post-processing stage to improve the quality of performance. For example, the soft shadow and Soft shadow, ambient occlusion, and glossy reflection effects need the filters to avoid noise. These two images below show the ray trace result on our mobile platform. The last one is the application with heavy computing. We expect that the ray trace effects are pre-compute or show the results progressively. Lots of pre-compute technology are developed in past decade, such as pre-compute radiant transfer, radiosity, and so on. Developer can use our framework to build their own one. Some heavy computing ray trace effects can also achieved progressively. The final result can accumulate over time. For example, the dispersion of diamond, the caustic of glass, and the indirect lighting in a room. The ray tracing API in our SDK. Our SDK is built on Vulkan language, and we choose to support the Rayquery API. Our ray tracing API is compatible with Vulkan ray tracing extension. Why did we choose Rayquery as our ray tracing program interface? It's because it's easier for developers to integrate it into their program. No additional rendering paths or the rendering pipeline is required. Developer only need to add their ray tracing logic to their existing shaders. The ray tracing lighting result can simply add into the final pixel color. A quick summary. MediaTek Ray Tracing SDK can enable the ray tracing capability on our next generation chipset, Dimensity. Our ray tracing functions are based on Vulkan. We support Rayquery API that is more friendly for developers on mobile, and it is compatible with Vulkan extension. The SDK will also provide some post-processing functions for ray tracing effects. Our tool can help developers to debug by visualizing the complex dependency of Vulkan objects. Thank you. Let's hand over to Am.
In conclusion, ray tracing is coming to mobile games. In fact, Rayquery implementations are possible on mobile devices right now, as shown by the Tencent and ARM demos. Even though it is only a software implementation, it can do things such as shadows, ambient occlusion, and even reflections. To help make Rayquery development possible, ARM have developed a Vulkan layer that can enable devices to use the Vulkan Rayquery and acceleration structure extensions in their applications. And we welcome any early engagements with developers looking to explore ray tracing in advance of hardware support for mobile. Tencent have showcased their hybrid Rayquery application, which demonstrates an advanced solution for developers looking to achieve representative performance. And finally, MediaTek introduced their software development kit, which aims to aid the ecosystem in developing applications that use this technology and the tools surrounding it. Thank you all for listening.